Good morning, good afternoon, and good evening to everyone. Welcome to another educational webinar organized by A&G Neuro. My name is Marnoush. I'm the head of education, and I'm delighted to be moderating today's session on rapid EEG with dry electrodes, signal quality, reliability, and comfort. Is the technology ready? I'm honored to introduce today's speaker, who is also a dear ex-colleague of mine, Dr. Patrique Fiedler. Patrique studied electrical engineering and information technology at the Technische Universität of Ilmenau. Subsequently, he received a doctorate in the field of biomedical engineering in 2017. He then switched to industry from 2017 to 2021 and took on development, project, and product management positions. In addition, he's been a visiting researcher at the University of Porto in Portugal and the University of Pescara-Chieti in Italy on several occasions. In 2021, he returned to academia and was appointed junior professor with tenure track and head of data analysis in the life sciences group at the Institute for Biomedical Engineering and Informatics at the Technische Universität of Ilmenau. His research focus areas include data fusion and analysis of multimodal datasets and body sensor networks, as well as research on novel sensor concepts for biosignals and online capable analysis methods for close to hardware and close to sensor data processing. This session will be followed by a short demo of waveguard touch by Dr. Roman Bakhachev, the application specialist at A&T Neuro. And like always, we will have a Q&A session in which we can activate your microphones to have a more interactive session. In the meantime, please feel free to pose your questions already in the questions chat box in the course of the presentation. So without further ado, let's get to the presentation. Patrique, thanks a lot for accepting our invitation to be here today, and we are all ears.
Thank you very much, Manoush. Thanks for the invitation and also for the very kind introduction. And of course, a warm welcome to everyone in the audience to today's webinar. I will talk about the research, the developments that we have done throughout the last years in the area of dry electrodes for electroencephalography. So I asked myself, what are the typical questions that come to your mind, that come to our mind, when you want to know whether these dry electrode technologies that are now available also on the market, so have been transferred from research to commercially available products, are they actually ready? What are the constraints? What are the applicability fields or the fields of application? So actually, I will deviate a little bit from a traditional conventional scientific talk and answer or focus on a number of questions which I listed here. So what should you expect? We will answer the questions, why do we actually need dry electrodes and for what? What are the requirements for dry EEG electrodes? What are the signal quality metrics that one should expect in comparison to gel-based, conventional gel-based silver chloride electrodes? Do dry electrodes have more movement artifacts? Are they more susceptible to movements during subject movement or even mobile acquisitions? How comfortable are dry EEG electrodes? Of course, a major concern of many users actually, and in many applications. Is it easy to apply dry electrodes? What should I do with noisy or bad channels? And finally, what are the dry EEG electrode fields of application? I will always pose each of the major questions initially and then give a rather short, straight answer, followed by a number of slides with the scientific details and the studies we have been performing to answer these questions. And on the bottom of the slide, you will then also always have a QR code in order to access more information, actually the full paper. So here I will focus in the webinar on the results of all these studies. If you want more details on the materials and methods, the most important I will introduce, but the details, please refer to the related publications. So why do we actually need dry EEG electrodes? Because they offer a faster, cleaner application, and they are basically the only electrode technology that can be self-applied by the user whose EEG should be recorded. Why do we actually need that? Let's have a look and step back and actually consider the current fields of application of electroencephalography. Conventional electroencephalography has been usually a more stationary, lab-based or lab-focused modality. It has been used for a wide range of clinical applications in diagnostics, but also in monitoring during therapy and rehabilitation. And of course, it has been extensively used for medical research in brain and neurosciences. But there is a tremendously increasing field of application, not only in the medical stationary research, and then of course the transfer to clinical applications, but also in the mobile and out of the lab recording sessions, recording environments. The most important ones, the most well-known ones, are of course the brain-computer interfaces that enable the user to actually use his mind without actually moving extremities, without moving limbs, without moving speech, but controlling devices, controlling robotic arms or spelling, for example. Neurofeedback in order to improve or alter your brain activity, your focus, your relaxation state in order to improve mentally. And then, of course, sports sciences, movement studies that study or that investigate the interaction of subjects in groups, in learning environments, in mobile environments, and of course in sports, both in competition, but also in cooperation. And of course, for research, for home site self-improvement, which is a huge topic also becoming increasingly, and of course also for medical environments or medical applications, home site monitoring is becoming more and more important. And the problem is, let's now focus or look at what conventional gel-based EEG offers. Conventional EEG electrodes are manually placed on each position according to, for example, the 1020 system. The electrodes can, of course, be integrated into textile caps to ensure right positioning and also ease the application a little bit, but the actual preparation of each individual electrodes remains a manual, time-consuming and costly preparation, cleaning and gel application process. That also implies that you actually need or require trained medical staff. For example, for 64 electrodes, you have to consider around 20, 30, sometimes even more minutes, depending also on the subject and the skin condition, to prepare a gel-based, conventional gel-based EEG. So this preparation process is lengthy. It causes additional stress to the subject, especially it is limiting in case you have a not fully cooperative subject or a subject that has an increased level of pain when you actually apply something to the skin on the head. And of course, and that is a major limitation, this preparation, especially if you consider high density setups, so increasing number of channels on the head, is prone to mistakes and unnoticed conductive bridges, which may falsify your measurements. Nonetheless, there's also the risk of skin damage and skin irritation, plus allergic reactions due to the gel or the application process. Summarizing, these conventional gel-based systems are inapplicable for very fast and specifically for self-applied out of the lab recordings. And therefore, dry electrodes have been investigated by a number of groups, and out there in the literature, in the scientific literature, there is a wide range of proposed concepts, proposed materials. I will not go into detail on all the concepts mentioned on this slide. Let's just consider there are, of course, the conventional wet electrodes, which are also considered gelled electrodes. There's a number of dry electrodes, specifically microstructured electrodes, which on the macroscopic scale are rather flat, so not applicable to hairy regions of the head. There are the rigid, conventional first dry electrode concept, so usually hard plastics coated or hard metals. They have been also commercialized. There have been dry electrode technologies on the market, but they are extremely uncomfortable. There is a high level of pain or discomfort caused by these individual pins. And then there is, of course, the fully flexible and the bottom line, which is the bristle electrodes, but also textile electrodes. They are nice, again, for flat or less hairy regions, but they have a problem to actually pass through the hair layer and contact directly the scalp. And we are to a major extent focused on the semi-flexible electrodes, multi-pin, spiders, or even spring-loaded. We have proposed, developed, and also transferred the so-called multi-pin electrode, which is visible on the left-hand side in the semi-flexible dry electrode range here, and allow a completely dry EEG recording. Due to some limitations, which we also will be talking about, there have also been proposed the hybrid electrodes. We will not focus on those today, which apply a very small amount of liquid, a small amount of electrolyte, even too small sometimes to actually enable a reliable contact. So they are to some extent combining the advantages of dry and wet electrodes, but unfortunately they are also combining some of the disadvantages of both of the concepts. So we will focus on the semi-flexible multi-pin dry electrodes, and I will discuss the fields of applications, the constraints, and of course the questions that come to your mind once you want to use these electrodes in your research. Given I cannot go into detail on all the materials and methods for each of the studies we perform, let's just summarize. There are multiple studies. You will find the QR code on the bottom, ranging from 16 to 115 healthy volunteers in each case, so no pathologies investigated in these studies yet. 6 EEG centers worldwide supported the studies, and overall 7 operators. All of the EEG measurements were performed sequentially, so always gel first or dry first, and then counterwise, the other electrode type, not at the same point in time. And we usually used for addressing and evaluating the signal quality a standard EEG paradigm involving eye blink artifacts, involving spontaneous resting EEG with eyes open and eyes closed, and involving an evoked potential, specifically a visual evoked potential with a checkerboard pattern reversal. In each of the studies, we also many of the studies, we also investigated the preparation time, which was measured from the initial application of the cap on the head up to the moment when the actual EEG recording started. So when the operator was considering the measurement ready to perform the EEG experiment. We asked the subjects to evaluate the wearing comfort on a scale from 1 to 10. This is important to note. 1 is maximum comfort, 10 is maximum discomfort, so you actually want to take it off if you evaluate with 10. We measured the electrode-skin impedance, primarily because that's a very common question also, and there have been thresholds in the literature in the past, but we also investigated the channel reliability and the interrelation with the impedance. So coming to the first question, what are the requirements for dry EEG electrodes? And that is, of course, rather straightforward. You want comfort, signal quality, and rapid application. That's what you expect. That's why you actually use dry electrodes and not gel-based electrodes. And in fact, there are some more specific requirements, including also biocompatibility. The easy application implies that the shape must be passing through the hair layer easily and allow a rapid reproducible application with a high level of wearing comfort. The signal quality implies also that the electrode coating material must be electrochemical stable, especially in contact with human sweat, which can vary a lot in composition. It must be compatible with the amplifier, specifically mobile amplifiers, especially if you want to use it at home or in mobile setups. And then there must be, of course, skin contact stability and producibility if it should become a commercial product. And there are actually multiple aspects of a system, namely, or of the electrode firsthand, the coating material, which is actually acquiring and transferring and converting the signal from the surface of the head to the actual electronics, the substrate material, the substrate shape, and of course the cap system. All these electrodes are integrated into. And as you can see, the different device components plus the requirements are strongly interconnected. So you cannot improve just on one aspect. You have to consider all of them and develop a comprehensive system that can actually be produced and also fulfill all these individual requirements in the best way possible. And that is, of course, something which has been done in the past, and therefore products are available on the market. But as with every technology, development is continuing. So there are new and improved technologies also coming. Where do we stand today? What signal quality should I expect from the available electrodes? Basically, you can expect equivalent signal quality to gel-based electrodes in the conventional EEG range from 1 to 40 Hertz. But you have to also consider increased channel dropouts. I will go into detail on these in a minute. Let's first go into detail on the signal quality. Let's look at the spectral domain, the frequency, the power spectral density in the frequency range from 1 to 40 Hertz. And what we can see here for the spontaneous EEG in the upper and the middle row is the comparison between the gel-based recordings in blue and the dry recordings in black. Recordings performed here with the 256 channel high density EEG system. And what we can see is that both the median, which is the solid line, and the standard deviation, which is the dotted lines, strongly overlap. So there is no major difference in the power spectral density in this frequency range. We can also see that easily if we look at the lowest plot here in this slide, which actually shows the differences between the respective eyes open and eyes closed, gel-based and dry recordings. So for the whole frequency range, we can expect similar signal quality. We can expect similar spectral characteristics. We have also performed statistical tests, and they showed minor differences in lower frequencies. So sometimes in some of the studies, there are differences for frequencies between 3 to 5 Hertz. We are currently investigating what the root cause is. However, this was not reproducible in all of the studies. So in most of the studies, we did not find statistically significant differences in the whole frequency range. One reason for the small deviations in lower frequencies could also be eye movements. Most of the artifacts have been taken out before the analysis, but slow movements, of course, could still induce activity. And we are, as I mentioned, investigating further. However, as I said, for the most of the frequencies and all the good channels, you can expect equivalent signal quality with no statistically significant differences. For the evoked potentials, we saw the same effect, actually. No statistically significant differences, both in amplitude, here for the N75 and P100 component of the visually evoked potential, but also for the latency. You see in the lowermost plot a slight difference in the latency. This is actually caused by the stimulation system, not by the electrode devices. And even this small difference here was not statistically significant across the population. So again, we can record equivalent signal quality with both dry and gel-based dry electrodes, whether in spontaneous EEG or in evoked activity. If we then calculate the signal to noise ratio for the main components, N75 and P100, again, you see the distribution across the subjects is very much overlapping, very much similar to each other, no statistically significant differences. And then, of course, specifically if we talked about high density EEG, one want to look at the spatial domain as well. So let's first look at the spatial domain of the visual evoked potentials. We see here the potential distribution of the main components, N75 and P100, again, in the upper row for the dry electrodes and the lower row for the gel-based electrodes. And again, we see no major differences. In order to look into that in more detail, we actually calculated the differences, which you now see in the lowermost plot. And again, we performed a statistical analysis assessing whether there are significant differences on individual electrodes or in individual areas. And the red areas that you see here actually have shown a statistically significant differences. These areas are below 5% of the overall areas. And actually they comply, or they are placed very much on the border of the cap. So where adduction is reduced and where any type of movement, we will talk about that in more detail later, actually induces differences. So in the major areas, specifically in the central areas where we have the main potential differences for our investigated VEP, we have no statistically significant differences. And we can do the same thing in the spectral domain, actually looking at the power spectral distribution in the topography of the alpha band. And we see nicely the alpha activity in the posterior and occipital region, both for the dry and the gel-based electrodes. No statistically significant differences for less than or for more than 95% of the area. Again, we see some small red areas on the right-hand side in the difference plot. Again, these are on the rim of the cap, and it is below 5% of the overall area. So why do we actually have differences? Let's first look at the channel reliability. Channel reliability was manually evaluated by EEG investigators, and they actually graded each recording that we performed. So eyes open resting state, eyes closed resting state, visually evoked potentials, eye movements. They graded the signal quality for each individual channel in each individual subject and each individual test. And then overall, we calculated these topographic plots for the gel-based on the left-hand side and for the dry electrodes on the right-hand side. And what you can see is that in the central and parietal region, we have a slightly decreased channel reliability, but overall, we have a channel reliability usually across all the studies of 75 to 80%, sometimes even 85%, depending on the exact paradigm. We might have an issue with the adduction on the central region, which we will talk about later on. But 75 to 80% of the channels work in most or in all of the studies. And therefore, for these 75 to 80% of the channels, you have these equivalent signal quality we already talked about. Does this actually comply with the electrode-skin impedances? Let's first look at the electrode-skin impedances, because conventional EEG has this threshold of 5 to 10 kilo ohm. However, this was actually established for very old EEG amplifiers in the 80s, 90s. Technology has evolved significantly, and today's EEG amplifiers can work with much higher electrode-skin impedances. For dry electrodes here, we talk about an average of a few hundred kilo ohm. However, as we saw, even with these dry electrodes in the order of a few hundred kilo ohms, we have a high channel reliability and we have equivalent signal quality with state-of-the-art EEG amplifiers. We again see a slightly increased impedance level specifically for the central and parietal regions, likely related to adduction, and a reduced impedance level at the frontal and temporal areas. Do electrode-skin impedance and channel reliability actually correlate? We investigated that, and we found the correlation of channel reliability and electrode-skin impedance only for impedances above roughly 850 kilo ohm. Below 850 kilo ohm for the given setup, there is no strong correlation. So the correlation value is below 0.7, below 0.6. No strong correlation between high impedances or impedance level in general and the channel reliability. So maybe 850 kilo ohm could be considered as a threshold for future studies. Do dry electrodes produce more movement artifacts? No, in case of slow or homogeneous movements. Yes, in case of transient rapid movements. That's really an important aspect to consider. If you have transient movement, fast accelerations, then yes, you will see stronger artifacts. You will see more artifacts in the dry EEG. But we have been performing a study with dry EEG also during movement in a cycling experiment, which you can see on this slide and which was published by Difonso et al. In 2019. And we actively investigated with two different layouts, and one equidistant and dry, and the 10-20 setup for the gel-based setup. We investigated how the alpha activity of the individual participants shift in an exhaustion experiment. So basically they were cycling, and during the whole cycling before and during the whole cycling experiment, we recorded the EEG and calculated the alpha peak frequency. It's a known effect that with exhaustion, physical exhaustion, but also mental exhaustion, alpha peak frequency may increase. And we actually found this for both of the dry and the gel-based electrodes. We can see it in this plot. The X indicates always the individual alpha peak frequency for each individual subject prior to the exhaustion experiment, so before cycling, and then the circle actually indicates at the end maximum exhaustion. And we can see for most, basically for nearly all of the subjects, of these 13 subjects here, we have an increase of the individual alpha peak frequency. And we also checked whether this increase, this change is actually statistically significant. And yes, it was significant for the condition prior, so resting before the cycling, at the end, maximum exhaustion, but also at the recovery afterwards. But there was no statistically significant between the two electrode types. Between the exhaustion phases, yes, but that was expected. That was the case, or the actual point of investigation, but there was no difference, again, between the two electrode types investigated. Alpha peak frequency consistently increased after physical exhaustion. And we had another very interesting finding in this study, because it was the first study where the subject actually had a different task than to actually just perform resting state EEG and the visual evoked potential. They had a task they actually focused on, which was the cycling. And for the first time, the wearing comfort reported actually increased at the end of the paradigm, which we attribute to the fact that they were not focused on the electrodes all the time. They had a different task, actually. That brings us to the next question: how comfortable are dry EEG electrodes in general? And we can answer they are sufficiently comfortable for 1 hour of wearing, and we are working on increasing the comfort further in order to allow even longer recordings. Let's first look at the preparation time versus comfort. We performed a multi-center study. I will show a bit on more details in the following slides also. We performed a multi-center study with several institutions worldwide and different levels of experience of the operators. And what you can see is that the preparation time, of course, varies across these centers, varies also across the experience level of the operators. But we roughly have a preparation time for the gel-based 64 channel caps in the order of 30 to even 40 minutes, depending also on the subject. While for most of the dry recordings, dry EEG, we are in the order of 10 to 15, sometimes 20 minutes. So 50% reduction of preparation time. The comfort, however, which we see in the lower plot, also decreased. Remember, 10 is the least comfort, 1 is the best comfort. So comfort decreased for the dry electrodes. However, we will look into that. We will look into detail on the following slides. The comfort was always in the range below 5, so always in the range where you can actually record up to 1 hour. In the meantime, we have also introduced and developed a number of improvements regarding comfort compared to the first dry electrode concepts. We now have different lengths. So for the less hairy regions, we have reduced pin length, which contributes to more comfort. For example, on the frontal or forehead region, you don't actually need pins. You just need a slight wavy structure for some remaining hair. That was integrated and is also available in the commercial products now. Over time, how does wearing comfort actually evolve? Comparing the gel-based in blue versus the dry recordings in black, we see that the gel-based comfort remains in the area between 2 to 3 on our 10 scale, while for the dry recordings it decreases, so the value actually increases over time. But even after 60 minutes, we are still in the better half of the range, so still bearable, still a usable comfort. That's why I showed or discussed that 60 minutes, 45, 60 minutes is usually an application time that can be performed with all of the subjects. And we have a second study actually performed and published in 2021 by our colleagues in the Netherlands, by Jana Hayes. She has investigated a new cap with softer electrodes. So softness also contributes to more comfort. And what we can see in the second plot on the right-hand side is that the dry comfort values are closer already to the gel-based EEG, still at the beginning, but also at the end, so after the EEG recordings, which were also in the range of 1 hour and sometimes even a bit above. So with softer electrodes, one could improve also the comfort. And we are actually now working also on improved shapes from the straight pins going to angled pins that will further improve the comfort and allow much longer applications and wearing times, we will submit the publication in the coming weeks. It's actually already finished. Plus, we have for the first time also been able to record dry EEG in lying positions. From the perspective of application, one should also consider how much adduction is actually needed, and we performed a study on that in 2018, and we can see that even for softer electrodes and harder electrodes, there is a threshold per electrode, roughly around 2 Newton, between 1 to 2 Newton, which we need to have a sufficiently low impedance, in this case here assumed to be an indicator of contact reliability. So 2 Newton should be roughly applied to have a reliable contact with the skin. And if we look at the comfort that corresponds to the adduction, we also see that comfort, of course, with increasing adduction decreases, but if we are at 2 Newton and let's say below 4 Newton, we are always in the lower half of the range, so always in the comfortable region. So between 2 to 3 Newton is what we actually need for each of the electrodes to have a reliable contact and therefore stable signal quality. That is, of course, sometimes a task, an issue, a difficulty when you talk about caps, different head shapes and different hairstyles. That is a matter of training then. So how easy is it to apply dry electrodes? It is easy, yes, with training and experience. We have, as I mentioned, performed a multi-center study in 6 countries with 7 centers or 7 operators. And as you can see on the column number 2 and 3, the head circumference and the age range was comparable across all the sites, but there is a difference in the experience level of the operators. Specifically, I would like to raise your attention to the data set 6 and 7, where the experience level of the operator, both for gel-based and for dry recordings, was less than 1 year. They were introduced to both before the study. Looking at the preparation time, we already talked about it in detail. As I mentioned, roughly 30 to 40 minutes for the gel-based system, while we have 12, 15, sometimes 20 minutes for the dry electrodes. And then at the reliability, this heavily depends on the operator. And here we see data set 6 and 7, the least experienced operators, provided a significantly reduced reliability, in this case of only 60 and 55%, compared to the more experienced operators, so data sets 2, 3, 4, and 5, with a reliability around the 80% I already indicated for most of our study. That highlights the importance of training and experience, given that the head circumferences, the hairstyle did not differ across the centers. We need to attribute it to the training state of the subjects. So what should we do then with the noisy channels, with these 20% of bad channels? And the answer is straightforward: signal processing. There is one signal processing related aspect. When it comes to high density EEG, one can consider spatial oversampling. So if you need a certain spatial resolution, one could actually place a few more electrodes. This is not a problem, given that you don't actually extend your preparation time, given you are using dry electrodes. So use more electrodes, higher spatial density than actually required, and this actually gives you the opportunity to lose some of the channels, but still have the sufficient spatial resolution already in the raw EEG data. For low density EEG, there is an even easier solution. You need a specialized setup or headset. If you have low density, then it also becomes much easier to apply the dry electrodes and compensate or ensure the right adduction at each individual electrode site. Consider that most or all of our studies have actually been performed with 64, 32, 64, and 256 channels. So these are all multi-channel setups. For some of the applications we have been discussing, brain computer interfaces, neurofeedback, you don't need this high density. So you could have a simplified setup, less channels, and then it also becomes much easier, much faster again to apply these dry electrodes. If you actually have the channel dropouts, you need to apply signal processing. If you cannot compensate with higher spatial resolution, you need signal processing. And we cannot go into detail in this talk about all the available algorithms. There's a wide range published internationally. I would simply like to show here the effect of the spatial filtering with the SFARA algorithm that has been proposed by our group in the year 2015 and is also implemented in commercial software. In the meantime, we see here a typical dry EEG recording, both on the left-hand side, spontaneous EEG recording, on the right-hand side, evoked activity. And we see some nasty bad channels floating around, and we apply the spatial filtering. So it's not an interpolation. We do not interpolate. We do not artificially calculate data that is that was reduced or taken out before. We really spatially filter the overall sensor data, and we can significantly reduce, basically correct the bad channels, which you can see here in the corrected recordings, again, for the spontaneous EEG on the left-hand side and for a visual evoked potential on the right-hand side. If you want more details on the SFARA algorithm, but also other types of algorithms proposed by our group, I would like to refer you to our website and, of course, the reference here, Greichen et al. 2015. So finally, what are the dry EEG electrode fields of application? Where can you actually use it? You can use it for short, repetitive, or self-applied EEG. Let's look again at our increased range of EEG fields of application. Dry EEG is not intended to replace gel-based EEG in each of these applications. That is not the aim of dry EEG. Dry EEG enables specific new fields of applications and eases certain fields of application, specifically medical emergency EEG, where it really time counts, time matters, where comfort is not your major concern. You can compromise comfort. Most of the subjects or some of the subjects might even not be awake, and you can actually record a dry EEG with the right amount of reduction and therefore with an increased channel reliability. Tele EEG, where you don't have all the materials, all the trained stuff for gel-based EEG in each of the remote sites, but an instructor that actually enables the remote sites to apply a dry EEG cap where you actually only need the amplifier and the cap itself. Then, of course, research applications, those fields, those paradigms where you need a rapid preparation, where you sometimes have very short paradigms of 35 to 45 minutes, where the subject doesn't accept longish preparation times, or where it is simply not efficient. If you have a short paradigm of 30 to 40 minutes or even less, you don't want to spend 30 to 40 minutes just for the preparation and double your overall time. And of course, for repetitive measurements. So maybe not long-term continuous measurements, but if you want to measure at repetitive instance of the same day or on multiple days, on multiple subjects, group analysis also, of course, then you don't have the time to prepare a gel-based EEG in each individual case, in each individual subjects in a group study, or multiple times a day. In those cases, you usually also have very short paradigms of a few minutes only, and that is a typical application, a typical repetitive measurements application for dry EEG. And then, of course, there's all these home side applications where you have the subject, the user applying the cap him or herself. So self-application is a major requirement, and self-application with the gel-based system is simply not possible. So in summary, where are we? Yes, the technology is ready for these outlined fields of applications. We have 75 to 85% average channel reliability in all of our multiple studies. You saw all the references. We have a reduction of preparation time of 30 to 60%, and we have sufficient comfort for 45 to 60 minutes of application. Several improvements like softer electrodes, improved shapes that are not using straight pins anymore are in progress and offer or promise much higher increased comfort that also will extend the applicability range of dry EEG further while not compromising on signal quality. We found no statistically significant differences in the signal quality comparing the gel-based and the dry caps among most or the majority of our investigated signal quality metrics. And especially as an outcome of the multi-center study, there was no direct relationship between preparation time and comfort. So just spending more time doesn't increase the comfort or decrease the comfort. Of course, it increases the application time. So if you prepare too long, then you might compromise your recording time. Preparation time and channel reliability. Again, longer preparations times do not necessarily increase the reliability. It depends on the training and experience of the operator. So yes, dry EEG is ready. Dry EEG can be used for certain fields of application where gel-based EEG is not applicable, but it is not yet plug and play. That is a common misconception. Dry EEG can be faster if you have the experience, but it still requires training, it still requires experience, and you have to consider the channel dropouts, the bad channels, as I mentioned, either using spatial oversampling, specialized headsets, or post-processing with advanced signal processing algorithms. With this, I would like to close the webinar. Thank you for your attention. Thank you to you in the audience, but also thank you to all of our collaborators, students, research colleagues worldwide that have been supporting the development, but also the validation studies and the application studies for the dry electrodes, which I have been using today in the webinar. Thank you very much.
Thank you, Patrick, for this brilliant, informative, and objective presentation on the usefulness and readiness of this newly developed technology, in which you're absolutely the frontier.